Okay, let's work through problem 2 in your lab packet and see how to work this one out. I've already gone through and filled in the shorthand notation for the mother's chromosomes just based on the phenotypes. Of course, the father's chromosome will always be recessive, little g, little d, little t. I don't write that down, but that would also be here as part of the diploid genotype. So I'm really focusing on the alleles that came in on the mother's chromosome. And we have the numbers here I've already highlighted. In yellow I've highlighted the parentals, and in green I highlighted the DCOs. So you would circle and label those. And that's just based on the numbers. 422 and 398 are the biggest numbers. 2 and 1 are the smallest numbers. So then you need to figure out what gene's in the middle. And you're going to look at your two parentals. In this case, you have big G, big D, big T on one chromosome and little g, little d, little t on the other. That's in your mother. And when you look at the DCOs, this one's not too hard to visualize since the parentals have an all-cis configuration. If you look at the two DCO chromosomes, I think it's fairly easy to see that if you flip the Ds, if you put the little d up here and the big D down here, that would create the allele combinations in your two parentals. So, because D is the one that needs to be switched in the DCOs, if you want to recreate the parentals, then D should belong in the middle of the map. And it's already there, so there's really nothing you have to do. So what you want to do then is write out your mother's chromosomal layout the way it would appear. So I'm going to do big G, big D, big T on one chromosome and little g, little d, little t on the other. And maybe space it out a little bit. Ugh. It's not too easy on the keyboard. So let me space this out. So maybe like that. So if you were looking for a segment 1 crossover, it would be a big G with a little d. So segment 1, looking for big G with little d, or little g with big D. So I go through my data and I look for that. Big G with little d, so that's a no, but that's a yes, so a 31. And then this is a no, but this is a yes, so a 2. And then little g, big D, right there. Oh, and a big G, little d. Big G, little d, and a 1. And 28. So those are your 4 numbers. You do that divided by 1,000. I'm just going to do like this. And you will get 6.2% recombination frequency. Oops. So that's for segment 1. For segment 2, you'll be looking for a big D with a little t, or a little d with a big T. And when you go through the data, so big D, little t, so right there 52, 2, 1, 66. So you'll notice that it follows the pattern. You have 4 numbers. 2 of them are your DCO numbers and 2 of them are single recombinant numbers. Divide by the total, and that is going to be 12.1%. So your map It's kind of hard to draw. You can put G, oops, D and T out here, and then segment 1 you'll indicate a 6.2 map units, and for segment 2 you'll indicate 12.1 map units. Then it asks you what's the allele configuration of the female parent. This is your female parent. You have all the recessives together, so that's all cis. So G, D, and T are all in cis, or all in a cis configuration. It doesn't matter, but I try to do this lowercase letters. All right, C of C and interference. Coefficient of coincidence, first you have to calculate expected DCOs. And expected DCOs is going to be the recombination frequency of segment 1, but use the decimal. Don't do 6.2, do 0.062 times the recombination frequency in segment 2 times the total, which is 1,000. And you would expect 7.502 DCOs. You observed 3. So your coefficient of coincidence is the ratio of observed over expected. So you observed 3, you expected 7.502. And so your C of C comes out to be just about 0.4. I think it might come out to be like 0.3999 or something, but 0.4 is good, close enough. And then interference is 1 minus C of C, so that'll be 0.6 or something very close to that.